Welcome to this tutorial video on the anatomy of HDFS Write. My name is Shivam, and in this video we'll explore the key components and steps involved in writing data to the Hadoop distributed file system. At the heart of HDFS is the Namenode, which acts as a central authority for managing the file system metadata. The Namenode keeps track of the files, directories, and their respective locations in the cluster. This is called a block report. It ensures data reliability and availability through replication, which we'll explore shortly. The replication factor determines the number of copies of each block that HDFS maintains across the cluster. In this case, the replication factor is set to 3. Now, let's take a look at the cluster layout. The cluster is divided into racks. In our example, we have 4 racks. Each rack consists of multiple data nodes, which are responsible for storing the actual data blocks. In our example, there are 16 data nodes, with each rack having 4 nodes each. The data nodes are labeled with their respective IDs and store and serve the data blocks under the supervision of the Namenode. When a client wants to write data to HDFS, it interacts with the cluster through the writing client. The writing client initiates a create request to the Namenode, indicating its intent to write data. Let's see how this process unfolds for multiple blocks. For each block, when the Namenode receives a create request from the writing client, the Namenode assigns a unique ID to the block and determines the location where the blocks should be replicated. The writing client then sends the data block to the first designated data node for storage. This is the data node which is generally the closest to the client, but that is not a mandatory requirement. The further replicas, the number of which depend on the replication factor, are placed in accordance with the replication strategy. The default replication strategy in HDFS is to create 3 replicas of each data block, with 1 replica on the same rack as the writing client, or if the writing client is outside the cluster, then a node is chosen randomly. Although Namenode tries to avoid nodes that are too full or too busy, and the other 2 replicas are placed on a different rack. This strategy is known as rack-aware replication strategy. By placing replicas on different racks, the HDFS ensures data availability and fault tolerance in the event of rack or node failure. This strategy provides several benefits, optimizing 4 main aspects of HDFS operations. First, reliability. By storing blocks on 2 different racks, the rack-aware replication strategy ensures data reliability. In the event of rack or node failure, the data remains accessible from the alternate rack, reducing the risk of data loss. Next, write bandwidth. When writing data to HDFS, the writing client only needs to traverse a single network switch to reach the designated data node on the same rack. This reduces network latency and improves write performance, as the data does not need to traverse multiple switches or racks. Read performance. When replicas placed on different racks, HDFS provides a choice of 2 racks from which to read data. This improves read performance by enabling parallelism and load balancing. And finally, block distribution. The rack-aware replication strategy ensures that each client writes a single block on its local rack. This approach distributes the block evenly across the cluster, preventing any single rack from becoming a bottleneck. And that's the anatomy of HDFS Write. We have seen how Namenode manages the file system metadata, how data blocks are replicated across racks and data nodes, and how the writing client interacts with the cluster. If you found this video helpful, please consider liking this video and subscribing to my channel for more such informative content. Don't forget to leave a comment if you would like me to discuss any specific topic of your choice. Thank you so much for watching.